we're going to make the session as interactive as possible. So feel free to ask any question. So what I'm going to share with you is probably more experience that we had in the US. Give you a little background of Wells Fargo. Some of you may not know Wells Fargo. We are among the top 4 largest bank in the US. Particularly, we are the largest commercial bank in the US. So some of you probably a little bit too young. When I understand Wells Fargo is when I was very young, when the TV is still black and white at that time, and I watched cowboy movie. It had John Wayne and it has Wagon that get robbed. That's how Wells Fargo Wagon basically. That's how old Wells Fargo is. A bit sharing some of the experience today and the focus, because in the US, bank is heavily regulated, and the regulators check our model all the time. And so what I'm sharing with you are part of the responsible, part of the ethical AI. We're going to talk about that and how to look into this. One of the Sivan will talk about explainability. I will talk about explainability as well, because that's core and center about with what we do. So first of all, bank runs by model. If I can share with you, we have a few thousand models in Wells Fargo. We have about 1,400 data scientists in Wells Fargo. There's about 1,000 people in the US and about 400 people in India. And a quarter of the people that do our data science split into two groups. People who build model, and then a quarter for every 3 model developer, we have 1 model validators, independent. They report to different groups. They are fully independent. This model validator are people who check model, test model, and approve whether model can be put in production or not. So let's think about that. For every 3 model developer, 1 independent model validator. Think of its model validator as, if I'm using the IT terminology, yeah, it's not tester. It's not. Tester is the job of model developer. Model developer is the computer hacker. People who are going to break the model, show how bad the model will be in what situation. And I'm part of the talk that I'm going to talk about today is all models are wrong. When they are wrong, they create damage. If it's financial model, it's going to create financial loss for banks. If other model, that's non-financial model, it can create reputation damage, hurting people. So we'll talk about that a little bit. So we use model a lot. Why we use model a lot? Because bank is data rich. Banks, even money is just information. Bank is moving information, moving bits. Right? It's all about information. It's very data rich. And also because of very data rich, decision is very data driven. We have I mentioned before, we have a few thousand models that we run day in and day out. And the other side of banks, because you're moving information, bank is very process intensive, very process heavy. From somebody applying loan into delivering the loan and delivering the fund. It's all the way very process intensive. Because it's very process intensive, it's very natural to automate many of those processes. So that's part of it, why we use a lot of model. And when we use model, it falls into 2 areas. One is financial model for financial purpose, credit approval, for trading, for anything, liquidity, managing liquidity, etc. Including in the US, every bank has to go to stress testing. Basically, we run about 600 models to stress every aspect of the bank, from how much money we're going to lose, into revenue, into expense, everything you name it. We run that twice a year. So that's it's like the World Cup of modeling. That's when people run models. So a lot of financial model, of course, it has financial implication. The other side is non-financial model, customer service from, let's say, I lost my credit card, You make a phone call, or you do something, you are unhappy, you make a phone call, you complain. All those things listened by model and routed to the right people who can handle the complaint. Or if you making a phone call, will be your voice will be monitored, will be heard, the voice biometrics, the background noise, the phone brand that you're using, the line, and where you are calling from, and then the people who answer the call will see whether this call fraudulent or not, right? Whether this call fraudulent or not, the people will answer it. Let me tell you about the responsible AI a little bit because it was mentioned. Let's say something very mundane about a phone call. Yeah, and you say, okay, because this look fraudulent, you need to go to a branch to show your ID so that the transaction that you have can be released, right? So sounds very innocent. But what happened? Somebody like me, who speak English with very strong, very thick Indonesian accent, or somebody they are not English native speaker, somebody speak with Singaporean accent or with Mexican accent, and if those call flag to be more with higher fraud score, right? With higher fraud score, what happened? Model is discriminatory. You use higher fraud score, you have to go to a branch to show your ID, you have to go to a branch, you miss a few hours. It looks very innocent. For you and me, probably just annoying that you have to go to a branch. But think about the subpopulation people in the US, that they have to work 2 jobs or 3 jobs to provide to their family. Miss work mean not feeding family. Yeah. So this is why it's so important when dealing with all of this. When we're working on this, not only the model can create damage. We'll talk a little bit more of that. So this is why I talk about why model risk is so important. Building model, having model is just the starting point. It's the easiest part. Now the question is, what can go wrong with this model? And what are the unintended consequences, like I talk about discrimination, right? Is all models are wrong. We know all models are wrong. When they're wrong, like I said, it creates harm. If it's financial model, it's financial harm. So first and foremost, think about what can go wrong. So before my life as a data scientist and lead data science team in banking, I've been in banking for many years, but my first life, my first career, I was a design engineer. I used to manage engine design for Ford Motor Company for North America. I have a team of 300 people who design engine for Ford Motor Company and designing part of the design. So what happened when you design? You're not only designing product that will perform, that will function. What happened when the car crashed? We want to make sure that people don't die or hurt least. So we always think about product safety. When we design machine learning, when we build AI, it's always think about model safety. Yeah, so that's the financial model is very it's very simple. I say market risk for hedging is hedging lose money. Well, we don't want to lose money, but at least you know it's money losing. We have to think about. If you think about a year ago, some of you probably heard about a company called Zillow in the US. Zillow is a listing company. If you want to sell your house and all those things, then they start into a business of buying and selling house because they think they can predict house price so well, and they are very, very proud of their AI model, the so-called Z estimate. Yeah, and they got clobbered, and they have to lay off a third or a quarter of their people and close their business of that piece. Yeah. Now in the US, there's a very proud AI company. They think they do it so well. driven by AI. Now in the US, when you have model incident, your model doesn't work, people say, make sure that you don't get zeroed. Okay? Make sure that you don't get zeroed when you build model and deploy model. Okay? Because from a proud AI company becoming a laughing stock on the street. Yeah. A few examples. Let's say online marketing. How many of you apply online marketing model? Recommender system. What can go wrong with recommender system? It just click. At worst, people don't take. What happened? I get so infuriated all the time when I use Facebook because I get offer of certain medication. I never declare my health condition, yet they know they offer it. So violation, very, very blatant violation of privacy, because you're always looking at the cookies here and there, what website you visited, and etc. In the US for banks, and you heard a few months ago, Facebook get fined on the discriminatory of their offering, right? Their marketing. Banks will be subjected to that too. If you offer, because people, older people, younger people, they browse website, go to internet very differently. Then you make product excluding certain product offered to certain demographic. That is discrimination. So we want to make sure, if we think about online, the problem with model is privacy and fairness. Big deal. Big deal. You can go wrong, and you in the US, it's we got in the spotlight all the time. If we lose the reputation, if we have reputation damage, what I'm worried the most is not that our model failed and we lose money. Yes, we worry about that too. But what I'm worried the most is our model get picked up by Wall Street Journal or by Bloomberg and say, well, Fargo model is racist, discriminatory. We will have a new CEO in the US. They will get called by Congress and you have to meet a new CEO. So that's kind of reputation damage that we have to deal with. Credit approval for lending, that's a credit approval. I'll give you an example here how sensitive this one is. Credit approval, use a credit card approval. You apply credit card or go through model, get approval or not approved. Just give you a simple example. One of the very predictive variables is mortgage size. How big the mortgage that the person has. Because the bigger the mortgage, the bigger the house, the richer the person. We cannot use that variable in the US. To approve credit card, whether approved or not approved, you cannot use the mortgage size. Why? Because mortgage size is discriminatory. In the US, mortgage size is racist. So you discriminate between white and black in the US if you use mortgage size. So as data scientists, we have to think a lot about this all the time. About what can go wrong, what the unintended consequence. And we know our models are wrong, and this is the one thing that we learn as well throughout the financial crisis in the US. The model works. Model works when people don't need models. Okay? In a good time, you can just give credit to anybody. It will perform well. The model typically, most of the time, don't work when people need the model during crisis. When we really need model to help, model won't work. That's the type of thing that we need to think about. Build model that work the best under the worst condition. Did we think about that when we build model? Build model that perform the best under the worst condition. Unfortunately, most of us, and almost all AutoML too, build the best model under the best condition, not under the worst condition. Because you split the data into two, I'm assuming the world are the same, never change. So let me optimize my model given the data that I have. So you're building a wrong model because you're building a model that will not work when we need it. So in the US, this is an area that very heavily regulated because if model wrong for big bank like us, the model bank in trouble. That is create financial havoc to the nation, financial instability, just like in the 2008. The 2008 crisis was blamed on the model, the infamous Gaussian-Coppola model. We have it today too. A lot of fintech in the US imploded. The so-called AI fintech imploded, right? Because they built a model that performed best during the best condition, which we don't need that model actually. You can just approve any loan. Okay, so in the US, we are thinking always it has what we call it model risk. David, hell is full of good meaning, but heaven is full of good works. The road to hell is paved with all the good intention, right? So we build model, try to do something, but it turned out model create more trouble during the time when we remake model. So in the US, it has called SR 11.7, OCC 11-12. That's why in the US, in the Big Bang, for every 3 model developer, it has 1 model developer, the hacker, that's going to show how bad the model will be in what condition. Okay, so that's the and always think raise what can go wrong. Testing, prevention, and mitigation. So we know exactly what the model will go wrong before going to production. We know exactly how the model will perform well, perform bad, in what condition. So that when the model not working, we know exactly what to do. So 2 years ago, when COVID-19 hit, many models not working, but we know exactly what to do. So no panic, because we know exactly what to do, because models are tested under different conditions. That's the theme that we're going to talk about today with some example. So because this is what the real world, I tried to put a cartoon here, model impacted by many different things, particularly environment. And when model into production, shit always happen, right? When put model in production, shit always happen. Shift data drift. Have you test your model under data drift, under distribution chains, under all of those things? Those need to be tested before model put in production. Then of course you monitor it. You don't let go, you don't let loose model put in production before all this testing. So I'm going to share with you some of the testing today. Okay, so when we talk about key element in model validation, we talk about 2 things. One is conceptual soundness of the model. Is the model make sense? Is the model make sense? So this part of explainability, interpretability, causality is the input-output, this has causal relationship, and overfitting. All machine learning overfit, all of them. All machine learning, when I'm talking about machine learning, are really ensemble model, gradient boosting machine, random forest, or deep learning. All of them overfit. You just detect it. If you simply random sample it, you won't detect it. We'll see it later. But when distribution shift happen, when data drift happen, then it show up. The model overfit, the model doesn't work, the model degrade very, very quickly. So that testing are very, very important. And then of course, outcome analysis. The outcome analysis, we have a few things. For example, we look at the error analysis weakness. This is the problem with the data science approach in general. We look at model, we judge model based on the performance, based on metrics. If it's a prediction regression model, we base on the mean square error, prediction error. When we do classification, we probably do look at accuracy, look at AUC, at 1 score, and all of those things. The whole complicated data, we model it with the complicated machinery, machine learning, and we measure it using average, one measure. That's terrible. You know why terrible? Because that's a measure of average. When shit happened, it happened at the tail in the region. Do you know which region, which area, in what condition that the model performed worse? So part of the example, we're going to talk about that. We talk about robustness. This is very, very key and important, robustness. We know data is noisy. When you build model, you clean up the data, you do all gymnastics on the data. You do imputation, you clean it, you remove outlier, and all of those things, you build model. Model that nice working under perfect environment. Real world data is noisy. It has error, it has noise. So if you don't test model robustness, you choose model that perform best under very squeaky, clean, hygienic data, you put in production model perform really, really bad. We'll show you that later. Okay? Model reliability. Reliability is about confidence. Our confidence about with the decision, with the confidence about the prediction, confidence interval. Area prediction that has wide interval are area that are less reliable. Area that has very tight confidence, narrow interval model, we are confident with that. Have we tested? Do you know in which condition that the model will have high uncertainty? So uncertainty output is very important. Resilience. How resilient the model when environment change, when interest rate going up significantly, when COVID-19 hit, is the model going to work? So the model need to be invariant. Model need to still working under changing environment. So a lot of time in machine learning, people say, oh, I'm going to retrain my model all the time. If needed, retrain it every day. Or all the time, real-time retraining. That's typically is an excuse of lack of robustness, is an excuse of lack of resiliency, is an excuse of overfitting. Because you're fitting noise, so I have to retrain it all the time because the noise changed. Okay? Have you tested the model? That model will be resilient. The model will work when we need it. And of course, I'll talk about bias and fairness. Okay? AutoML. This is the language that, the tool that every data scientist loves, but it's also the dirtiest word. Because a lot of things can go wrong with AutoML. Okay, now here I give an example. We train, I have a chart here. On the horizontal line is model complexity. Model complexity, if you build gradient boosting machine, is deeper tree and more boosting. Yeah, boosting it more, and tree is also deeper. Okay, that's an example of model complexity. So what happened? You split your data into two. Most of the time, what you see, you have model and more complex. The training error will go down, right? Like the one at the top. The training error will go down. And when you test it with testing data, what happened? More and more complex model. It will go down too. And most of the time, it will stay flat or even better. So what happened with that? It's no overfitting. In machine learning, it's almost no overfitting. Or even if it's overfitting, it's very tiny, it's not ample. So when we do AutoML, where's the AutoML going to choose? Somewhere in here, maybe? Because with 0.001 improvement, you win Kaggle competition, right, Shivam? Yeah, you will be in your higher Kaggle rank. Okay, that's what you choose. Okay, so we'll see later in machine learning. So you can have a lot of many models that perform almost the same, but yet they are very, very different models. That's why explainability is important, to see which model that makes sense to look at explainability tool. We're going to talk about that a little bit, but explainability tool can be wrong too. If you go in that situation for highly critical model, we don't do a post hoc explainability tool like SHARP and LIME and all those things. We don't do that. We build model that inherently interpretable. We're going to go through some how to build sophisticated machine learning, including deep learning, that is inherently interpretable. That we can see exactly what the model does, right? So the other thing is what we're going to see later. This model, more and more complex. Think about this. Some of you familiar with 3, right? If I have 3 depth 7, those you have 2 to the 7 leaves, 128 leaves. So if you have data, each of data point will fall into that leaves. One of those leaves, either 1 if fall to that leaf or 0 if not. So if you have 3 that depth 7, you converted your original variable into 128 variable, 0, 1 variable. Now you boost it 1,000 times. So now suddenly you transform your data into 128,000 variables. And then you do linear regression on that. That's what gradient boosting machine is, basically. Okay? The number of boosting times the depth of 3, that's equivalent to 1 hot encoding of that number of variables. 128,000 variables. And your data is only 20,000. Clearly, you have more variables than your data. Your model will fit everything perfectly, but you will still see this. No overfit, it don't show up, okay? But it will hurt later, you will see it later, it will get hurt later with robustness problem, with slight changes on the input. That model that's best, crumble. Become model that's worse. We'll see that in an example. Okay, let's talk about explainability first. When we talk about explainable machine learning, we talk about intrinsic interpretability, model that inherently interpretable, and model that with a post hoc explainability. This bottom is a black box model. Then we apply all kind of techniques, LIME, ICE, PDP, SHARP, and all of those things, right? The one at the top is really how to engineer model, sophisticated model, not logistic regression, not decision tree. We're going to talk about gradient boosting machine. We're going to talk about deep neural network, but still inherently interpretable so that we don't need post hoc explainability. So why is that? Let me give you an example on this one. Why deep neural network is inherently interpretable. Shivam is putting this application in H2O wave, right? Shivam, I'll put this one. So I'll give an example. The neural network is a glorified local linear regression. Okay, no more than that. I'll give you an example. So I have a network. You see a very small network here, 2 layers. Okay, the first layer is only 2 nodes. So one node is on. If you have data, node 1 on, or node 2 on, or both nodes on, right? When node 1 on, because of ReLU, it's linear. It's on, so it's a linear equation on that. If the second node also on, another linear model. Combination of 2 linear model, still linear model. Yeah. So you can trace neural network for every data point. It will generate into linear model, into local linear model. It's just many of them. It can be 1 million of them, depending on the size, but it's local linear model. So no more than that. ReLU, deep ReLU network, it degenerates into linear model locally. So what deep ReLU network does is basically splitting the data into many different regions, and each region linear. Okay. So here's an example. Can we rely? Then people typically apply that apply 3 deep ReLU network is a black box model. Then apply LIME, SHARP, or integrated gradient or anything. So here is I pick an example. This is using very simple model, simple data, California housing price, and you give an example here for if you compare, because deep ReLU network, it has ground truth. For each data point, we have linear model, and you can see they don't match. Okay, this is LIME, this is SHARP. Okay, they may not agree to each other. If you look at the left and the middle, they don't agree with each other in terms of the variable importance. and they can be totally different with the ground truth. Okay, so if you look at here an example, latitude and longitude are the most important variable. Actually, the real thing is longitude and median income. So post hoc explainability can be wrong. The more complex the model, the post hoc explainability will be more in trouble. So this is the dilemma. People try to explain using techniques of explainable AI, very useful, by the way, but need to be used with caution. It's not 100% trustworthy. And for high-risk application, I would avoid using post hoc explainability. For high-risk application, design model that inherently interpretable, we're going to see that a little bit later. Deep ReLU can be inherently interpretable, so you can use deep ReLU and then you can regularize it. So when we look at designing interpretable model, we need to think about two parts. One is the feature selection. The second one is the model architecture. The feature selection, it has to be very meaningful. The input can be meaningful. It cannot be just combination of input to feature engineering, automated feature engineering that doesn't make sense. It needs to be meaningful. It needs to be causal. You need to check. Is the relationship causal? I'm going to do some example on causality. Regularized feature. We cannot put everything. We have to really select variable that is well regularized. Same thing on the architecture. We need to make it. We need to control the architecture so that it's becoming interpretable. Okay. So here's an example of how to create model that inherently interpretable, and then I go to one example. Then we see. So we can create using functional ANOVA decomposition to construct model that follow this model that inherently interpretable. So there are several examples out there. One of them I call explainable boosting machine. I think H2O have this in that. The other one is the counterpart of that, but using neural network, scanning neural networks. So you can have model that we know exactly how its variable perform, how they interact to each other, and so on and so forth. So there can be done, that it can be done to build sophisticated model that is inherently interpretable. Let me go to a few examples on this one here in terms of robustness. Okay, remember we do AutoML, we choose the best model. So this is an example. So I built 3 models. One is using using XGBoost. Second, using ReLU network. The third one is model ReLU network, but I regularize it. I apply L1 regularization so the network becoming simpler. If you look at the performance here, you run your AutoML, you look at your leaderboard, which one is the winner? XGBoost. So you pick XGBoost, right? Because the vertical line is mean square error. The smaller, the better. So you run it, you run your AutoML, you look at your leaderboard, which one you pick? XGBoost, right? What happened with you put in production? The model doesn't work as well. Always, when you put in production, your model doesn't work as well. If your model you put in production work better than your model development, it's just complete luck. Okay, but typically you put it model. So this is an example. When you apply perturbation to the input, yeah, you apply perturbation, just a tiny perturbation on your input, and then you test it with that. Look at what happened with XGBoost. It's become the worst. Right? Become the worst. This is a model that you have to retrain all the time because of overfitting noise. So with the small perturbation, the model perform quickly, degrade very quickly. So this is a very example. This is all the time you will face with this all the time. When you build model, then try to perturb it. Put a random noise in your input, and then calculate the performance. Compared to model alternative that is simpler. If you actually run it with model with shallower tree, less boosting, the performance will be less under ideal condition, but when you perturb it, it will perform better. So this is the danger of AutoML. Because AutoML is going to pick this. So your AutoML need to be the starting point, cannot be the end. It's another example in terms of resilience, how the model will perform under distribution shift. So in this example, is the data is shifted. So how the model will perform? You get degrades very, very rapidly, the performance. So this is another test that you have that people have to do when build model. How to test under distribution shift. I'm going to pick this one here. This is a typical thing will happen in the model building. People build model with all kind of variables. All of those, any tiny bit will improve the model, you put it in. Remember complexity of the model? You improve it, you get it. Here's the model, there's a problem here. Okay, let's say I have variable X, E, and Z, and the response is Y. So what we do, we build model with all of those as input. But it's actually E impacting X and X impacting Y. So what happened with this? And this is real case during COVID-19. E is the environment variable. That E changed. When E changed, E shifted, your model performance degrade very rapidly. Okay, because it never see that E is outside of the distribution that the model have seen. So when you expose that, the model degrades very quickly. But if you test the causality, E impacting X, E not given X, E is not impacting Y. We test given X, E not impacting Y. Okay, so E should not be in the model. If E not in the model, E change, E will drive X, X will drive Y, the model still work. The model will be resilient. So testing for causality is very important if we need model that will perform under different conditions. So let me, some of you that want to try, we put educational packets out there to learn all this concept. I walk through this concept very quickly, but this is what we do in model validation. So if you want to get a little bit taste, visit the GitHub and try it. It's very easy to use. It's an educational tool to use the interpretable, inherent interpretable model, and with all those robustness testing, reliability testing, resilience testing, all of those are in there to give a better understanding. Let me stop right there and let me have a question and answer here, about 5 minutes, then I'll turn it to Sivan. Go ahead.
So is it always true that for a simple model, it's much more robust than a complex model? Has there been any strong evidence on that?
Very good question. The problem is always no free lunch. Yeah. So first, you need to get a good model under ideal condition, right? If simpler model, the performance is way off, you get robust model, but it didn't perform well. So the key is you need to get model that perform well and robust. So think of it, some of you that's in the understand optimization. The problem of building model for real world is not problem of creating best performance model under best condition, but creating best model under worst condition. So it's a min-max optimization problem, minimizing error under maximum worst condition, right? So min-max, so it's a trade-off. So if you have several modeling alternatives, then you look at it, you need to look at, okay, here's a model that perform best under ideal condition. Here are model that will be more robust. So the question becomes, is this different acceptable? Right? Is this different acceptable? And then how bad, how sensitive to the perturbation? So it's a trade-off. When we build model, it's not single objective. We need to build model that's robust. We need to build model that's resilient. Model that's also work under many different situations. Model that's also fair and unbiased, right? So it's a really trade-off of multiple objective thing. This is why the AutoML using single objective is misleading. You need to use AutoML single objective as starting point. Okay, I got a good candidate. So now let's say good candidate, the performance probably is a little bit worse, but maybe it's more robust. I pick that. So I'm not going to pick the top in the leaderboard. And that's very sensitive to the choice of hyperparameter. Very sensitive to the depth of the tree, very sensitive to the number of boosting if you use boosting. In neural network, very sensitive to the number of layer and the number of nodes. So in neural network, you apply L1 regularization to simplify it with different L1. In that example, it has ReLU DNN with larger L1 penalty, with smaller penalty, and then you choose which one. Does that make sense?
Yeah. So the other question I have is related to feature engineering.
Yes.
So you said that, so as far as I know, is there any very developed method that does causality based feature?
Yes. So this is actually interesting. The easiest way to do, let's say you build XGBoost model, okay? And you have the variable importance. Then you do backward elimination. You do causality test. So you can do RCOT tests or RCIT tests, many different causality tests that you can apply. If I remove it, condition on X, is this independent? So you do backward elimination. Okay.
So how about the sparse feature selection methods like L1 regularization or stuff? They typically don't work well. Okay.
No, those are simply based on correlation, not conditional independence. What we need is conditional independent tests. Many open source tools right there like RCOT, RCIT, and many open source independent conditional independence tests that you can apply. The simplest thing is just you eliminate one by one from the least important variable. Okay, because that model will be more resilience. The model that you use everything that you gain 1 digit, second digit, or 3 digit improvement. If you do Kaggle competition, of course, you don't want to eliminate, you want to win it, okay? But if you want to put model in production, then you need to do all of these things carefully.
Thank you.
Where do you see the next level of 5 years, 10 years? What would be the technologies that would help you overcome the problem?
Yeah, I think it's this is very active. If you look at, I think it's Duo is working on this, putting some of this tests in there. A lot of the open source community building all of this as well. The one that I showed you before is our version, the PyML. So you do PyML toolbox. Those are all in there. So you can stay tuned as well because we're putting more and more testing in there. But this will be next and will become easier and easier. I'm hoping the software provider will put attention and build all of these things. Yeah. So, but I think right now a lot of open source. You have to go to several different open source. Look at the PyMLs. We released the PyML early this year to try to educate people and have all the tools in there. But it's really an open source that we try to grow. So our team releasing that, but it's very active. Many people working on this subject and putting open source tool out there. All right. Yes.
If we are using real world data and if you are using sufficient data, then why are we assuming that the model is not robust?
Because your real data that you have is, you assume is static. When you split it, yeah, when you split it, data, random splitting, the two models have the same distribution. The two data has the same distribution. If you histogram it, you histogram your testing data and training data, histogram it, it will be on top of each other. Okay? Real world is not like that. I just gave you a little bit example before. Real world is like this. You have shift. Today, how do we handle this? Today, the way we handle it, We put the monitoring, right? All the ML ops is becoming a cottage industry. A lot of company offering monitoring, but that is we putting model that's not robust and cross our finger and let's monitor. What we need to do it more responsibly. One step before we put in production. Test it under distribution shift. You can create this, by the way, very easily. When you build model, you purposefully remove some sample in certain area instead of random sample. Build your model and test it, right? So people do this all the time as well. Let's say I'm going to do out of time testing. I'm having data from out of time. I built data from last year data and I tested using data from 2 years ago or whatever. So you assume it has distribution shift, but that's not rigorous enough. So what you need to do, you need to introduce deliberate shift and then you test it and to see it. You deliberately introduce noise. This is what happened all the time. Like say, suddenly Andrew talk about, hey, data-centric AI. Let's focus on the data. That's kind of funny to me, you know, because it's always have to be data-centric. So Andrew built a model that doesn't work. You put the vision system, the training data using this camera. You put it in production, a different camera, different noise. Model doesn't work if your model is not robust. Data from one hospital, you apply it in different hospital because the procedure are different. It's different. It's not going to work. So those kind of things happen all the time. A lot of failure in machine learning and AI is because of this lack of robustness, lack of reliability. Does that make sense? So we have to deliberately, if you have the data big enough, then you can resample it in different way, deliberately, to exclude some of the data from the training from other buildings so that you can test it. For example, I give you some simple example. Very, very simple example. All of you do K-means clustering. Okay, I do K-means clustering. I cluster it into 10. Okay, and I remove one cluster. Okay, I'm going to build model using this 9 cluster. Then I test it with the cluster that I remove. Let's see how the model works. Okay, if you do K-fold validation, 10-fold validation, use 10-fold from K-means clustering. So you can see how the model will perform under different distribution. Very simple like that. Did we do it? I will bet 99% of you didn't do it. Very simple thing. All right, any other? All right, go ahead.
Oh yeah, I'm not sure it's like super related. It's when it comes to the transparency of the model.
Yes.
I think it was my background.
Yes.
I work with some insurance companies and
Yes.
they're expecting me to explain the model to
Yes.
them. So I feel like how do you like explain the model in a way that like people from a business background could be more understandable instead of people from a mathematical background?
Right. Well, first of all, mathematically, you have to be able to convince and explain yourself. Okay. If you cannot explain mathematically, it's no hope that you can explain it to the business, right? So how to explain it mathematically? Here it is. One example. Very simple model. Okay. I structured the model G0 plus GJ first term, GJX. Okay, if I stop right there, that model by statistician is called generalized additive model. It's H2OM, right? Generalized additive model. G is nonlinear, but one variable. So I can explain it, I can plot it, I can see it. So mathematically, you have to be able to explain it. So if I need, that model may not be good enough because you have variables that interact with each other. Well, I go to the second one because I have interaction. But it's very, very clean. I know exactly the interaction. I know exactly the function. I can see it, right? And so you have that. Now I'm going to put it into neural network. Then how you put it into neural network? So I'm not just feeding it into fully connected network. I'm going to build a network that is one variable, another variable, 2 variable entering, another 2 variable entering. Then I have a model that is very decomposable. I know exactly the effect of X1. I know exactly the effect of X2. I know exactly the effect of X1 times X2. So first you have to be mathematically understand exactly what your model does. So I cannot just feed it into a fully connected neural network. I cannot just run gradient boosting machine. If you do gradient boosting machine, here it is, one boosting on X. You need the boosting on this. You need boosting on this. You need boosting on this. You need boosting on that. Then your model is explainable. You have explainable boosting machine. You have explainable neural network. You know exactly what the model does. So you have to start from that. And then if you understand that, then you can start explaining to the business, does this make sense? The causality is also important because choosing variable, the causal is very important. So when I have people that build in machine learning models say, oh, I have 1,000 variables, I cringe. Because that mostly doesn't make sense. The model can do anything that doesn't make sense to the model for sure will not be robust. For sure, the model will not be causal. Okay. So building machine learning model for high-risk application need more thought. So yeah. So we can build model, architecture, engineer it. That is really make a lot of sense. So that's the starting point. Then I can explain it. If I can make sense, I understand the math, I understand it, then I can explain. If I cannot decompose it, applying Lime and SHAP on top of black box model is trying to explain the unexplainable. Okay? It's okay if the model is not high risk. Let's say I'm going to do it for fraud detection. Once produce fraud alert, somebody is going to investigate. It's okay to apply something like that. But if I'm going to use it to apply to approve or not approve credit, it's not okay. Because approving or not approving credit, deciding the livelihood of people and the family and probably their future generation. If it's applying to healthcare, your model may kill people because they may reject treatment. Then we're in trouble, right? So for high-risk application, build model that in terms of performance probably sacrifice a little bit, but it's more explainable. And by the way, it will be more robust too. So those kind of considerations that you need to think about in building model. All right, thank you so much. I'm going to turn it to Siobhan.